Good evening. I'm Mrs. Bolin with University of West Florida, helping my students with simple linear regression at the end of the semester, spring 2018. So here we go. We're going to be discussing linear regression, and linear regression is simply regression is a mathematical model or equation that states the relationship between two or more variables. A simple regression model includes only two variables, one independent and one dependent. The dependent variable is the one being explained, and the independent variable is the one used to explain the variation in the dependent variable. Okay? A simple linear regression model that gives a straight line relationship between two variables is called a linear regression model. This is the specific type of model that we're going to be discussing in class. We're going to be looking at two variables, an independent variable and a dependent variable, and we're going to hopefully be able to find a strong enough relationship between those two variables that when we plot the relationship between those two variables, we end up with a straight line relationship. When we succeed at that, we have developed a simple regression model. That's what we're going to be learning how to do. Okay, so let's talk about independent and dependent variables. Let me give you a good example. Right now, sitting in my driveway, in my carport, we have a Yukon. Last year, we had two Yukons. One Yukon was a 2013, and it had 80,000 miles on it. And that had a value, a monetary value, that was significantly greater than my other Yukon, which we still have, which is a 2000 model and has 417,000 miles on her. So, as you can see, a 2013 versus a 2000, or 80,000 versus 100 or 417,000 miles. Those would be factors that directly affect the value of those vehicles or the price that I could sell them at. Obviously, a 2013 would sell for more money than a 2000 model, and obviously a Yukon with only 80,000 miles on her would sell for a significantly more amount of money than a Yukon with 417,000 miles. So what that tells us is the price or the value of the vehicle is dependent upon the number of miles on the vehicle or the age of the vehicle. Okay, so the independent variable would be how many miles are on the vehicle, or the independent variable could be the year the vehicle was made. The dependent variable would be the price you can sell the car for, because the price that you can sell that car for is directly dependent upon the age of the vehicle and the number of miles on that vehicle. So our objective would be that we would be able to develop a simple regression model that's going to yield a straight line relationship between the two variables, let's say the number of miles on the car and the price that we sell the car for. Okay, that's what we're going to be attempting to achieve. So let's scroll up a little bit here and let's go over some definitions. So we have a definition here of what's called a scatter diagram. A scatter diagram is simply a graph in which data pairs, which we would mark as coordinates, x, y, are plotted as individual points on a grid with a horizontal x-axis and a vertical y-axis. Okay, we're going to be doing that in just a minute, so you'll understand a little bit better what that is. Then we have an explanatory variable. This is your independent variable. Okay, so this is your independent variable. Okay, so that's your independent variable. And then we have another one called and the independent variable, I'm sorry, is the x variable. So whenever we're talking about x and linear regression, that is your independent variable. Okay, so the x is your independent. Now we have another variable, and it's called our response variable, and that's known as y. This is our dependent variable. Oops. Okay, so that's your dependent variable. When we look at a scatter diagram, we can look for a linear relationship between x and y. So we have an example right here, and it says phosphorus is a chemical used in many households and industrial cleaning compounds. Unfortunately, phosphorus tends to find its way into surface water, where it can kill fish, plants, and other wetland creatures. Phosphorus reduction programs are required by law and are monitored by the EPA. A random sample of 8 sites, so that's important, so we'll highlight, oops, forgot that I wasn't in highlight mode. There we go. Let me get into highlight mode here. So a random sample of 8 sites in California wetland studies gave the following information about phosphorus reduction in drainage water. In this study, X is a random variable that represents phosphorus concentration. So X in this one is going to be phosphorus concentration at the inlet of a positive biotreatment facility. And then Y is a random variable that represents the total phosphorus concentration, there we go, at the outlet of the passive biotreatment facility. And right here we have our data, okay? So here's what we measured for X, and here's what we measured for Y. Now, when we, now we're going to go ahead and I re-highlighted blue for the independent and green for the dependent variable colors. We're going to go ahead and create our ordered pairs, and we're going to plot each of these. It's extremely important that these are given as a matched pair, that you keep them matched together. You cannot put the 5.2 with the 5.9 and then the 5.9 here with the 7.1. You must keep the 5.2 with the 3.3, the 7.3 with the 5.9, the 6.7 with the 4.8, the 5.9, 5.9 with the 4.5, and continue on. You must keep those as matched pairs. That's how you find out if there's a relationship. What we're saying is when I inputted 5.2, I got out 3.3, okay? And then we say when we input 7.3, we got out 5.9. So this is a function, and we're looking at the relationship between those. And so we would simply write our ordered pairs something like this. We would say the first ordered pair would be 5.2, comma, and then we'll put our dependent in green, 3.3. And that would be an ordered pair that we would plot. The next ordered pair then would be 7.3. So 7.3, comma, and then 5.9. And then 5, whoops, didn't get that color switched. .9. Okay, so then we would come up with our third ordered pair, which would be our 6.7, and 4.8. Okay, and then we would come up with our next one, which would be 5.9, 4.5. Our next one would be 6.1, 4.0. The next one would be 8.3 and 7.1. We just continue all the way down, okay? Now we would want to plot these points. So we're going to do this just as if it was an X and a Y. This is our X, this is our Y. And so we come over, we say 5.2. So here's our 5.2 and 3.3. And here's our 3.3. So this point right there is our point that is directly representing the coordinates 5.2 and 3.3. Our next point is 7.3. So 7.3 and then 5.9 and 5.9. So that is this point right here that's represented by those ordered pairs. Another ordered pair is 6.7 and 4.8. So 6.7 and right here to 4.8. Okay, so this point right here is represented by these ordered pairs. So let's look at this one right here. We have an ordered pair right here, 7.0 and 6.1. So 7.0 right here, and then the Y part is 6.1. Okay, so I think you've got the idea of how we make a scatter diagram, which is what we did right here. The benefit of looking at a scatter diagram is we want to look and see, can we fit a straight line or an approximate straight line between these points? And we can. Can you see that we've got a positive slope here and that we have an actual relationship? I think you can see that. So that's what we're looking for, is right here, is there a straight line? And so if there's a straight line, then we know that we have a linear, remember linear means straight line, relationship between the dependent variable and the independent variable. That's what we're looking for, because when we have that relationship, we have the mathematical ability to make a model so that in the future I can predict what the potential output would be for a particular input, and that's very useful and very beneficial. Okay, so our interpretation here is, by inspecting this figure, we see that as X increases, Y also increases. That would be the positive slope that I referenced earlier. Okay, let's go over a couple more definitions here. So we have the correlation, which is denoted as the letter R, okay? And the correlation is the number or numerical measure of a linear relationship between two variables. So it is a number that represents how strong is the relationship between the two variables. So if I said, I think the color of a car would be my independent variable, and it directly affects the price of my car, do you really think that I could say, oh, I have a purple car and therefore I can predict the exact value of that car? Or I have a green car, or I have a white car, and therefore you can take, Zachary, stop that. So if I have a white car, are you going to say that I can have a particular value? No, you're not going to be able to determine that. The color is not going to have any type of influence. So in that case, R is going to be, R as in our correlation, okay, is going to be non-existent. If it's very strong, then we have a number that indicates that it is a very strong relationship, such as the miles of the car would directly influence the price of the vehicle, but color would not. Another item that probably would not would be if the car had tinted windows. Okay? Do you really think that whether a car has tinted windows is going to be a good indicator of the price or the value of the car? Absolutely not. Okay? So what we need to know about R is right here. It falls between the numbers -1 and 1. If you calculate R and it is less than -1 or greater than +1, you have made a mistake. It's bounded by -1 and +1. Okay? The closer right here to 1 or -1, the stronger the relationship is between X and Y. So the indication that you have a very strong relationship between the dependent variable and the independent variable is by looking at R. And if R is either -1 or very close to -1, or positive 1 or very close to positive 1, that tells you that we have a very strong relationship between the dependent variable and the independent variable. If r is negative 1, there is a perfect negative correlation, which means that there's a perfect relationship that every time you increase your independent variable, you have a decrease in your dependent variable. So that would be an example would be the higher your miles go on your car, the lower the value is of your car. Okay, that would be a negative correlation. If r is 1, there is a perfect positive correlation. So a perfect positive correlation. So that would mean every time your x increases, your y increases. Every time your independent variable increases, your dependent variable increases. This is something that we would highly desire in investments, right? We would love to be able to put money into a mutual fund and be guaranteed every time I put money in that my returns increase, okay? So that would be something very desirable with a financial investment. There are 3 types of correlations. We have a positive correlation, which is when r is greater than 0. This implies that as x increases, y also increases. We have a negative correlation, which is r is less than 0. And this implies that as x increases, y decreases. That's miles go up, value of the car goes down. Then we have no correlation. R is equal to 0. There is no linear relationship between x and y. That's like saying I have tinted windows and my car costs $50,000. Who cares? It doesn't have any correlation. If you find out that you have a brand new Corvette and it's $50,000, that would be, more in line. But tinted windows has no bearing. So that would be no correlation. Then lastly, we have the value of r is the same for x, y as it is for yx. So it doesn't matter the order, the r is going to be the same. Now we have an example here, or not an example, we have a formula here, and it looks very intimidating, okay? Don't worry about it. You got this. Every single student in my class has this. I'm just going to break it down a little bit at a time for you, okay? So let me go into my magic ink so what I write doesn't stay. So right here, the very first thing is n. That's our sample size. How many people or how many whatever did we have in our survey? Okay, how many that's n, our sample size. No big deal. Then we have an x and we have a y. I need to make sure I'm in my magic ink because that's not disappearing. Let me undo those, make sure that those disappear. There we go. Alrighty, so we have x, which is our independent variable observation, and we have our y, which is our dependent variable observation. And all we're saying is for each x, we're going to multiply it by the appropriate y. That's all we're saying. So coming back up to our example up here, this is our x, this is our y. So we would say, what is 5.2 times 3.3? And then we would add to it, what is 7.3 times 5.9? And then we're going to add to it, what is 6.7 times 4.8? And we're going to do that for each ordered pair that we have, okay? For each one, we would do the multiplication. And then we would add it together because it has the summation sign that says we add those multiplications together. So we sum it up, okay? So we list our y in a column. We list our x, we list our x in a column. We list our y in a column. Now I'm going to multiply the two of them together, 5.2 times 3.3, and that gives me 17.16, because this right here says I'm multiplying x times y. Then I have, what is 7.3 times 5.9? It is 43.07. What is 6.7 times 4.8? That is 32.16. What is 5.9 times 4.5, that's 26.5. And you go all the way down. Then we're going to add all of these together. All of these right here, we're going to add together. So it's 17.6 plus 43.7 plus 32.16 plus 26.55 plus 24.4 plus 58.93 plus 19.8 plus 42.47, and that equals 264.77. That is how we get that number right there. It's this number right here. Okay, so next let's look at this, the summation of x. The summation of x simply means that I'm going to take every one of my x's and I'm going to add them together. So what is 5.2 plus 7.3 plus 6.7 plus 5.9 plus 6.1 plus 8.3 plus 5.5 plus 7.0? That total is 52. Okay, so the total there is 52. There we go. Alrighty, so that takes care of what is the summation of x. The next one is, what is the summation of y? Well, here's my y. So summation of y is, what is 3.3 plus 5.9 plus 4.8 plus 5.7, or I'm sorry, 4.5 plus 4.0 plus 7.1 plus 3.6 plus 6.1. That sum is 39.3. So 39.3 goes right here as the summation of y. The next thing we have to look at is we have our n right there. Well, again, our n is our sample size. So in this case, what is our sample size? It's 1, 2, 3, 4, 5, 6, 7, 8. So n would be equal to 8 in our current example. Okay, so n equals 8 in our current example. Our next item right here is, it says, what's the summation of x squared? This one gets my students at times, so follow me closely here. What we're saying is I'm taking my x and I'm squaring it. So grab your calculator right now. Okay, well, we'll grab our calculator. We're going to grab our calculator. Here's our calculator. I have my TI-84 right here. And I'm going to put in 5.2. What is 5.2 squared? It's 27.04. And you'll see right here I have 27.04. So it's very important that you recognize that each observation in my x column here, I'm squaring it one at a time. So 7.3, what is 7.3 squared? It is 53.29. So 53.29 right there. What is 6.7? 6.7 squared. That is 44.89. Do you see we have that right there? Oops. Right there. So that's how we get all of those numbers. And then after that, what we'll do is we will sum all of these numbers up. So 24.04 plus 53.29 plus 44.89 plus 34.81 plus 37.21 plus 68.89 plus 30.25 plus 49. That number is 345.38. So again, this symbol right here, oops, says I'm going to take each one of these and I'm going to square it. I'm going to take that and I'm going to square it. I'm going to take this and I'm going to square it. Once I've got them all squared, then I'm going to add them up. And I'm going to come up with this number right here, $345 or 345.38. And that number goes right in there. This number right here is not this number squared. A lot of students get confused on that. Let me show you that. So if I take 52 and I square it, I get 2,704. 2,704. This number right here is not 2,704, is it? So this number squared is not this number. They are not equal. And it's very important that you recognize the difference here. Okay? So then the next is going to be right here. We have right here we have the summation of x, and then on the outside of the parentheses we have this squared. So here we're taking each x and we're squaring it and then summing those together. Here what we're doing is we're taking each x and summing it together, getting our total of 52, and then squaring 52. Okay? So completely different. And then y, we have our y here. We have our n here, and then this is y squared. Y squared, what's our y? 3.3 squared is 10.89. Y is 5.9 squared is 34.81. Y is 4.8 squared becomes 23.04. And then we're going to add all of these up so I get the summation of y squared. My summation of y squared is 205.57, and that goes right there. Okay, so that goes right there. The last item that I need is, what is the summation of y? So here's my summation of y. So this is my y. We're adding it all together. It equals 39.3. 39.3 goes right in here, and then I will square my 39.3 because my squared is on the outside of my parentheses. Very important that you understand this. Okay. So in our example here, here's our formula, and we rewrote the formula right here, and we're going to grab each of the numbers from our chart. This is called a 5-number summary. So we have 1, 2, 3, 4, 5. This right here gives us our 5-number summary. We can do lots in statistics when we have those summaries there. Okay, so again, we said earlier that our n was equal to 8 because we counted 1, 2, 3, 4, 5, 6, 7, 8. Okay, so n is 8. So we have our n right there, and you can see I have 8. The next thing it says I want to multiply n by the summation of x times y. Here's my summation of x times y, and you can see right there I put in 264.77. Then I subtract off the summation of x. What's my summation of x? Here's my x. I add them all together. That's my summation of x. So that becomes 52 right there. Multiplied by my summation of y. Here's my y. Add them all up. There you go. Right there's my summation of y. And it's going to be all divided by the square root of n times the summation of x squared. So here's my x squared column. All of it multiplied by each other goes right there, 345.38. We're subtracting off the summation of x, 52, and then we'll square that. But this is the summation of x that we have within the parentheses there. Then we have multiplied by the square root of 8 times the summation of x, or y squared, summation 205.57 minus the summation of y. Here's my y, add them all up. Summation of y outside of that number, the squared. When you put that in your calculator, you're going to end up with 0.97. So we just now said that r is equal to 0.97. Well, 0.97 is really close to the number 1. So that tells us that we have a very strong positive, because that's the sign of the r, correlation, which tells us that as x increases, y increases, and it's almost near perfect. Okay, so it says, just like the graph implied when we looked at the scatter graph up here of the raw data. Here's our scatter graph of our raw data. You can see it's a line going straight up like that. Okay, as we have it says, just like the graph implied, the correlation is strong, is positive, linear relationship, straight line. The correlation does not imply causation. Doesn't mean that something caused the other. We're saying that they are related. Okay, that we can use one to predict the other. Okay. Now here we go. Let me click that off and get over here. All right, linear regression and the coefficient of determination. So the coefficient of determination. In this section, we will now come up with what is with the best fitting line to relate x and y. So let me. So the best fitting line for x and y. We have a definition, and it's called the least squares criterion. And it says the sum of the squares of a vertical distance from the data point x, y to the line is made as small as possible. So what we want to do is, when we're looking at the line, our line, if we can envision that our line is coming right through here, we would actually look at the distance from the point to the line, from the point to the center of the line, the point to the line, and we would measure that distance, and we would want that distance to be as small as possible. And when we have achieved a line that goes between all, or amongst all these points right here, when we've got a line that fits between the points, that has the smallest distance between each point in the line, then that's called the best fit. Okay, we have done the best fit in that case, and that's important for us to be able to do, because that's going to yield the best predictor. Okay, so back over here. Okay, so this line helps us qualify and describe the relationship between x and y's. We're going to use the notation y hat is equal to a plus bx for the least square line. That's an equation that you need to write down. Recall from algebra, b is the slope and a is the intercept. Note that y hat is the estimated response variable, the dependent. Okay, the dependent response variable. And you'll notice that this is not necessarily given in our standard form for college algebra. In college algebra, we would normally say that we had y is equal to mx plus b. So, but it's with addition, so order is not so important. This is our standard for our linear regression. Now we're going to build upon the table from the correlation that we had before, the 5 summaries table. In addition to the column that we have already found, we will now find the sample mean, x bar, and y bar. Then we'll have the slope of the regression is given by this formula right here. So here is our formula for the slope of the line. Again, looking at our 5-number summary up here, and we're just grabbing this information. We know what n was, it was 8. We know how to get our, pull off our summation of x times y minus the summation of x multiplied by the summation of y. All of that divided by n multiplied by the summation of x squared minus the summation quantity of x, the quantity squared. Okay, that is what b is going to be equal to. And then we have the intercept, a is equal to, so we have another line, or another equation right here, and that is equal to a, which is our intercept, is y bar. And what would y bar equal? Let's think about this for a second. Y bar would equal to the summation of y. That's a sad looking y, isn't it? Let's try if we can do summation of y divided by our sample size. That's all y bar is. And then we would have x bar. I should have a bar right there, y bar. And then we would have x bar, and that's going to be equal to the summation of x divided by n, just like we would do any other average. And we would use those right here to calculate our intercept. Okay, so let's do an example of this. Returning to our original example, compute the regression line. We need the sample means. Y bar is equal to 4.912. I'm having some difficulties. There we go. And x bar is 6.5. So first, let's find the slope. Here's our equation for the slope right here. Okay, this is our equation for the slope. And we're going to notice that we have our n, that's 8. If you go back to your notes, you're going to see that the summation of x and y is 264.77 minus the summation of x, 52, times the summation of y, which was the 39.3, divided by n, which is 8, multiplied by the summation of x squared minus the summation quantity of x squared. And that gives us 1.2691. and that is our slope. Now to find our intercept right here, A is equal to y minus b, y bar minus b times x bar. So we have from up here, y bar is equal to 4.912 minus our slope, which is 1.2629, multiplied by our x bar right here. Throw that in your calculator, and you're going to find that your intercept is negative 3.2964. Thus, our regression line is given by y hat is equal to negative 3.2964 plus 1.2629 multiplied by x. Don't forget your x right there. So this means that for every unit increase in x, we expect y to also increase by 1.2629. We can use the least squares line for prediction. So we have right here, whoops, we have interpolation, and this is the predicting y hat values for x values that are between the observed x values of the data. And then we have extrapolation, and this is interpreting y values for x values that are beyond the observed value, okay? The least square line may not reflect the relationship between x and y for values outside the data range. So what that means is this. If I develop a linear regression model for the age of the car and a price of the car that it can sell, let's say that my model was developed using cars that had between 150,000 miles and 300,000 miles. Okay, so my example is that the miles that my car had on it were between 150,000 miles and 300,000 miles. So the only cars in my sample had somewhere between that mileage on it in order for me to develop a regression model used to predict the value of the car when it sold. The extrapolation right here, what that means is I cannot accurately necessarily use my model to predict the value of a car that has 70,000 miles on it, okay? Because I didn't have any vehicles with only 70,000 miles on it in my data set. Likewise, I couldn't necessarily accurately use my model to predict the value of a car that had 400,000 miles on it, because again, I didn't have a vehicle with that many miles in my data set used to develop the model. Now, sometimes we don't have any choice and we have to use the best model that we have, and so we're going to be using extrapolation. That happens. But you also need to realize that it's not necessarily the best option. Sometimes it's the only option, okay? But sometimes you have better options and you should use those, okay? So let's go back to our original example right here. It says, suppose we want to predict y as a value for 6. Is 6 an interpolation or an extrapolation? Let's go back up. 6.0. Here's all of my x's. Well, there's a number 5.2, which is below 6. There's a value 7.3, which is above 6. So that's going to be an enter because that's in between, okay? So that is going to be an interpolation, okay? The next thing is then I treat this just like a function, and I'm going to plug in 6 for my x and run it through, and I find that when x equals 6, my y is going to be equal to 4.281. Suppose we want to predict y when it is equal to 5.0. Is this an interpolation or an extrapolation? Well, let's go back up and look. I think it's an extra. Let's see here. Because we have a 5.2, a 5.9, and a 5.5. But we don't have anything smaller than that. So that's outside our sample. So that is an extrapolation. but we plug it in. We'll plug it in right here. We'll plug in x equals 5 for my x right there. Run it through our calculator, and we get 3.0181. Okay, and that is the end. Oh, yep, that's the end of our lesson. And so you are now ready to go tackle your linear algebra homework. I hope that you learned a little bit more about linear algebra, and this will come in handy, especially for our finance majors. I know you're going to use this in your economics and things of that nature. So enjoy your weekend, and study hard as you get ready for your finals. Email me if you have any questions as you get ready for your finals. Have a good night.